I'd like to welcome everyone to this event this evening. I am Kirsten Frysinger, and I'm the chair of the Boulder, Colorado Renewable Energy Society's chapter. I also work on the board as co-treasurer for the state organization. And we are here tonight to talk about cold climate heat pumps with Hans Preiss. And I'm going to move through a couple of housekeeping issues really quick and get on with the presentation. I'll go for just a few minutes here, and then we'll be moving on to the presentation. I try to keep it brief. If you have any questions, I do have my contact information in this presentation, and we're going to send out a copy of the recording tomorrow. The event is being recorded, and we'll send out a copy of the event along with Hans has agreed to, it's okay to send out his slide deck. I'll do that in a PDF file. And we'll move on to the presentation. We're going to go till about 8 o'clock and open it up to Q&A. So please put your questions for Hans in the questions box, and we'll read those out at around 8 o'clock or so, and Hans will respond. And with a crowd this size, we may run out of time, but his contact information will be included in the final slide, and you're welcome to reach out to Hans directly. If you're already a member, thank you for being here. If you'd like to become a member, we do have information here about joining. And there is an introductory rate of $30 for the year if you're not a member already. If you're a returning member, it's $55, and we also have business membership opportunities. Our chapter and all the CRES chapters, if you're not in the Boulder County area, if you're in Metro Denver or Fort Collins area, Pueblo, Jefferson County, those chapters are also usually looking for members as committee members and volunteers as well. So please consider joining as a volunteer if you've got the time or the interest. We have a couple of events coming up here later this month. One is with NCRES, that will be a webinar event, and others with CRES, Jefferson County, and that will be in person. If you'd like a little more information, we do have our QR codes here, so please feel free to use the QR code to check out the meetups. We have our recordings all on our YouTube channel, and this QR code will take you right to our YouTube channel. Almost all of our events are recorded, so this is a great way if you missed the presentation or if you want to catch up on something that you think you missed while the presentation was happening, you're welcome to go here. And our policy committee is very robust. We're in the middle of the Colorado 2023 legislative session, and I looked today, and our legislative tracker is up to date. If you are interested in policy, if you're interested in seeing what CRES is supporting or opposing, the legislative tracker is up to date thanks to the policy committee, and we're very active. That's probably our strongest suit here at CRES. We strive to educate, work in policy, and promote economic development in the renewable energy sector, along with energy efficiency and clean transportation. But our policy committee is working hard right now, and that legislative session goes through May of this year. This is just a quick view of what the legislative tracker looks like. If you go here, you'll download a PDF of the legislative tracker, and you can check out information about the bills. All right, this is just a slide I include to let folks know a little bit about who CRES is. If you're interested, you can pop back in when you get the recording tomorrow. And just to let you know, we have we're going to do a conference again this fall. It was a great success last fall, and more information is going to be coming on the CRES conference. It looks like we'll be holding that again at the Jefferson Unitarian Church. Thank you very much, Martin, for hosting. And here's a little more information with our QR codes. If you need any of the stuff I just blew by, feel free to use the QR codes to get to our meetup, to find our email, and to get to the CRES website. And without any further housekeeping details, I am going to change this over give it over to Hans. And Hans, I'll let you introduce yourself, and hopefully our technology will cooperate.
Very nice, Kirsten. Thank you so much for the introduction. So welcome everyone. My name is Hans Preiss. Thank you for spending your nice Wednesday evening with us. It's a beautiful spring evening, and yeah, we are happy that you don't have anything better to do than listen to a heat pump presentation. Maybe you're sitting on your patio enjoying the nice weather. Certainly hope you do. A little information about myself. I run the company named BrightSense. We've been in business for about 10 years. We're up to 3 people now. We offer building science consulting, and we design mechanical systems, heating loads, cooling loads, fresh air ventilation design, and we are the Rocky Mountain area reps for Arctic hydronic heat pumps. That's what we're going to be talking about today. I have an engineering degree from Munich University back in Germany, and I used to be a product manager at Bosch and Buderus. That's where I was introduced to geothermal heat pumps, and I also managed cast iron condensing boilers, tankless water heaters, solar thermal systems, which gives me a really good background so I can help people pick the best mechanical systems for their applications. I have a passion for energy efficiency, and I want to help other people reduce their energy consumption, their carbon footprint, and heat pumps, as we will see, are a very good tool to get there. Just a couple of words up front. It's important to always remember that when we're talking about a building, a home, that it's a complex system. It consists of the envelope, the walls, foundation, roof, windows. The occupants play a role, what's happening inside the house. Appliances, certainly, like kitchen. There's a lot of heat generated in the kitchen. And then, yeah, certainly the heating, cooling, ventilation, and water heating appliances also play a big role. So all of those things need to be considered when we're considering, when we're talking about energy efficiency in a home. It makes a big difference if you have a log house, the wind is blowing through, or if you have a passive house that is super airtight with 18-inch walls, something like that. Yeah, I get the question quite a bit. I have a 3,000 square foot home in Eagle County. What kind of a heat pump do I need? And yeah, that certainly there's no answer, no correct answer for that, because we need to determine what the actual heating and cooling loads are before we can decide what heat pump is required. And for that, we will be looking at all of those elements here on the screen. A couple words on heating and cooling, or well, let's start with heating equipment. Yeah, there's boilers. Boilers heat hot water. Furnaces heat air. And there's stoves, wood stoves, pellet stoves. There's electric resistance heat, mats that can be embedded in a slab. And then there are heat pumps. So yeah, the first four units, pieces of equipment, they generate heat. Heat pumps, they don't generate heat. They move heat. They transport heat from one side to another. And yeah, we can decide in which direction the heat flows and what amount of heat we're moving. That's yeah, makes the heat pump special. What types of heat pumps are there? Yeah, we all have heat pumps already in our home. The fridge in our kitchen is a heat pump. It moves heat from inside the cabinet into the kitchen. That's why the refrigerator cabinet gets cold, and yeah, the back of the refrigerator is warm. Yeah, the air conditioners are heat pumps. Yeah, heat pump hot water heaters are also heat pumps, as the name says. Yeah, they absorb thermal energy from the ambient air around the unit and use it to heat the water inside the tank. There's air source heat pumps and there's geothermal heat pumps. Air source heat pumps, what we will be talking about today, they tap into the ambient air outside. Where geothermal heat pumps, they are connected to the underground soil and bedrock and absorb thermal energy from down there. Yeah, one of the advantages of air source heat pumps is that the volume of air outside is almost infinite. Yeah, so we don't have to worry about extracting too much energy. It's not that we are going to freeze up our front yard by doing that. But yeah, there's certainly yeah, the heat pump itself has a capacity limitation. How does a heat pump work? Well, it's the refrigeration cycle. Yeah, heat is being absorbed on one side in the evaporator, and then it is rejected where the refrigerant condenses in the condenser. Of course, yeah, this is oversimplified, this picture. In reality, our system, our heat pump system looks a lot more complicated. What I should also say is that the cycle is reversible, so it can be turned around, and then yeah, we can use the heat pump for cooling. This is more what our refrigeration system in a modern heat pump looks like. And this is, yeah, I'm showing this more for the geeks. Yeah, it's certainly not important to really understand what's going on here. I just wanted to point out, yeah, that we have a variable speed compressor, and yeah, it's a DC compressor, so it's most efficient. It can be controlled very precisely. And we also have, over here, we have a subcooler, which is kind of an economizer. Yeah, it pre-cools our refrigerant before it hits the evaporator. And this way, yeah, it's super cool and can absorb a lot more thermal energy at that point. Yeah, so that provides our efficiency, a significant increase in efficiency. Yeah, what this is called is the enhanced vapor injection technology, the EVI, that you might see in some brochures for heat pumps. So how does the heat pump transport energy, and how does the efficiency get calculated? And why is a heat pump considered renewable? Well, That comes from the fact that we are absorbing thermal energy from the ambient air with an air source heat pump. So we are tapping into the air outside where the heat pump is located, and we are absorbing thermal energy from that ambient air. So if you stand in front of the unit, have the fan blow towards you, you will notice that that air is colder than the air is absorbed or is drawn in on the backside of the heat pump. And that temperature difference that comes from the thermal energy that was extracted by the heat pump from that air and pumped into the house. So here, on the bottom in the evaporator where we're absorbing thermal energy, in this example, we're absorbing three units of thermal energy, and that is combined with 1 unit of energy that is being used to run the heat pump and the compressor. And the other 3 plus 1, they are available then for heating our house. So we're receiving 4 units of energy. We're spending 1, so 4 to 1. This would give us a 400% rate of efficiency, or a COP, a coefficient of performance of 4. If we are looking at this from a cooling standpoint, our usable thermal energy for cooling is these 3 units here. Because we will be absorbing those 3 units from the house that we are cooling. And so our efficiency is then 3 to 1, or 300% in cooling for a COP of 3. In normal operating mode, we can achieve about an efficiency between 200 and 500% is normal under regular atmospheric conditions. This is what a heat pump looks like when it's set up on the outside of a building. These are hydronic heat pumps. That means they heat and cool water. So we don't have refrigerant pipes going into the house like with a mini split heat pump. We have water pipes going to the heat pump and from the heat pump into the house. That makes these heat pumps really universal, because you don't need any specialty equipment, no specialty tools. Regular plumbing tools are sufficient. And we're also using regular plumbing and boiler accessories like ball valves and fittings and PEX pipes, for instance. We are setting the heat pump in our snowy climate here. We're setting the heat pump on a 24-inch snow stand, and the name already tells us why that is. We don't want the heat pump to get buried in a snowdrift, because then it would not have any air exchange with the ambient air anymore. We need some clearance around the heat pump, so we get good airflow, and the orientation is also important, but I'm going to be talking about that in a little bit. These heat pumps that we represent, they operate down to -15 degrees Fahrenheit. That's basically as cold as it gets here on the Front Range. Down at -15, we can still produce 125-degree water. In cooling, we can produce about 40-degree chilled water. And this, the 125, makes this heat pump really well suited for in-slab radiant applications, Also with products like Warmboard or EcoWarm, yeah, those are manufacturers. They provide products that have the radiant tubes already built in. Stable Up can work under certain circumstances, yeah, what I should point out is that hot water baseboard, yeah, is not a compatible distribution system. Hot water baseboard, as the name says, requires much higher water temperatures, 160, 180 degrees Fahrenheit. Yeah, it's not water that a heat pump can produce at this state. Because of the 125, yeah, these hydronic heat pumps are also not ideal for domestic hot water heating. We're going to be talking about that in a little bit again, but just at this stage, yeah, it would give you a really slow recovery, and yeah, that would be problematic. These are a couple of applications photos. Yeah, this is the radiant tubing that has been installed on this subfloor just before the concrete slab is going to get poured. So this is what the radiant system looks like in a brand new home. And here on the left-hand side, I've got some pictures of what Warmboard looks like. Yeah, it's a plywood panel that has grooves installed for the radiant piping, and they have an aluminum top layer that spreads the heat out a little more evenly. So yeah, you have less of a dead zone in between those pipes. The EcoWarm is a similar product, and the last photo is a picture from underneath, looking at a Staple Up Radiant with the aluminum heat transfer plates. Those are essential. Yeah, so the Staple Up, the name is still there, but there's no staples used anymore. These heat transfer plates, they are screwed to the underside of the wood floor. What we can also do with our hot or chilled water is use fan coils. In particular for cooling, fan coils are really function really well. We can certainly also do radiant cooling using the existing infrastructure in the slab, or with Warmboard or EcoWarm with chilled water. However, yeah, radiant cooling is really slow to respond, and yeah, in many, at least in highly efficient homes, we might need cooling only for a few hours during the peak afternoon, and yeah, for those systems, the radiant cooling might not be a good application, because yeah, it's just too slow. You would have to turn it on an hours in advance, where a fan coil responds really fast. So these are some examples. Yeah, these are basically mini split looking fan coils, and those can be combined with our hydronic heat pumps, if you already have a radiant floor, and yeah, those for cooling. This picture here on the left, it shows one of those high wall fan coils installed. A lot of people, they think, yeah, these are not very pretty, most aesthetically pleasing designs, but people typically tell me, yeah, they notice that unit the first week after they move in, but after that, they don't see it anymore. It doesn't bother them anymore. What's also available is a whole house unitary hydronic air handler. Yeah, this one, this type here, this works with fully ducted systems in case there's a larger cooling load. then this might be a good idea to employ one of these. Let's talk about some performance. Here are for the engineering folks, performance curves. The orange line shows the heating load of a sample house. Down at the bottom of this chart, we have our outdoor temperature, from -20 degrees up to 80 degrees. So at 60 degrees, our heating load in the home is really small. And the colder it gets, the greater the heat loss of the structure, and so our heating load goes up. This example here is of a house that has a load of 36,000 BTUs per hour at -5. So -5 is a little colder than our design temperatures here. On the Front Range, where we have a design temperature of 0. And the other three curves here, those are the outputs of the 3 Arctic hydronic air source heat pumps that we are offering. The smallest, the yellow one is the small one, the 35. Then we have this one is called the 50. It's the medium size, and the large one is the 60. The reason why those performance curves and the outputs, why those drop, is because as it gets colder, there's less thermal energy in the outside air that can be harvested, which makes sense. It's colder, so there's less thermal energy. The warmer it is, more thermal energy is available. So that's unfortunate. As our heating load goes up, the performance of the heat pump, the air source heat pump, goes down. But the performance is very well understood and is very reliable. So we can use this performance data to size our heat pumps for our systems very precisely. The points that are highlighted here, where those the heat pump output curves meet the heating load of the building, those are so-called balance points. And the significance of that is that down to this temperature, the heat pump is able to heat that building by itself without any help from a second heat source. Only when it gets colder than that do we need some supplemental heat. So these balance points are very important to know, and we calculate those for every one of our projects. In this case, we've got them calculated, spelled out up here. With the small one, the balance point would be 18 degrees. That's not a number that we would be satisfied with. We like to see the balance point at least in the teens, or even below that. So here with the medium-sized heat pump, our balance point would be 5, and the large heat pump has a balance point of 0. That would be a perfect match in our eyes. Here I have highlighted the energy. So this down to the balance point, this is the energy, the beige is the energy that the heat pump would provide to the house to keep it comfortable down to 0 degrees. Below 0 degrees, the blue portion here, that is still the energy that the heat pump provides. We only need to supply this green portion as supplemental heat. And then the yellow over here, our heat pumps, we said they are able to operate down to -15, sometimes a little lower, depends a little on the exact conditions. So if the temperature were to drop below that, then our supplemental heat would have to provide 100% of our load. Now another fancy chart. Again, down at the bottom, we have the outdoor temperature, in this case in 5-degree temperature intervals. And the significance of those columns is the number of hours in a year at these temperatures. And yeah, we develop these charts for every single one of our projects. This one here is for Denver, recorded at the Centennial Airport, and it tells us how cold does it actually get. Yeah, minimum over those 18 years was -16 degrees. Maximum was 100. The annual average temperature over all of those is 50. But what really is important to us is how many hours do we see below zero? Yeah, we see a few columns down here. Yeah, so there are a few hours and they add up to 37. It's not a lot. But yeah, we need to be able to heat the house during these conditions. Yeah, so what does this tell us? It tells us, if we had a balance point of 0 degrees, our heat pump by itself would be able to heat the house down to 0. Yeah, we would need supplemental heat during 37 hours. It's not a lot. Even if our backup heater is not as efficient as our heat pump, it would not break the bank. Basically, that's what this tells us. As I said, we collect these charts for every single location. Normally it's an airport where we can collect reliable climate data. This here top right shows Salida. Leadville at the bottom right, 170 hours below zero. Yeah, certainly can be expected at 10,000 feet. Telluride, relatively mild, only 18 hours. Yeah, actually less than here on the Front Range. It's pretty amazing. And yeah, Telluride at 9,000 feet. What do we use this for instance, is to calculate how many hours of supplemental heat do we need. In this example, the simulation said, we need 72 hours of supplemental heat and 2 hours of straight backup heat, 100%. And if we add all of this up, they're comparing how much energy does the heat pump provide, how much energy does the supplemental heat provide. The heat pump 99%, and an average annual coefficient of performance of 3.2. That's actually pretty phenomenal. That's a really good number. So this would be a very efficient system. And what this also spit out, the simulation, that 130 million BTUs are delivered to the house in form of heat. The heat pump would consume 12,000 kilowatt hours to operate, compared to 420 kilowatt hours consumed by an electric backup boiler. Operating costs roughly $1,500 per heating season. And a question that we get quite a bit is, so how many PV panels do I need if I wanted to offset that? In this case, it would require an 11 kW PV system for net zero. Let's jump a little bit into the hydronic side. Some piping diagrams I have prepared to give you an idea. What does a heat pump system actually look like when it's installed in a residence? This is a very simple system. We see the heat pump that sits outside and is piped to a buffer tank in the mechanical utility room. And then from there, we connect to our radiant. The radiant system is very similar to what our regular boiler system looks like, with zone valves, with thermostats, and so forth. So a very standard system. Here on the right-hand side, on the system side, I'm showing the electric backup boiler. Yeah, a lot of folks who want to get rid of their gas, they opt for an electric boiler. And yeah, those are very simple devices, basically like your countertop tea water kettle in a different package, in a closed loop system without moving parts. So yeah, really reliable, dependable heat source that is not expensive. Yeah, in combination with a heat pump, a really good combination system. Yeah, these diagrams, I should point out, are very high level. Yeah, we're not showing any safety devices, any ball valves, check valves, or anything like that. So this is not for the plumbing professional. This is just to illustrate how a system would look like. We have a heat pump controller here that has an outdoor sensor. Yeah, this heat pump controller, looks at our tank temperature here and then activates the heat pump in heating or cooling as needed. Here is a system where we're doing heating and cooling, radiant heating and radiant cooling. So yeah, very similar. The only difference really is that we have a cooling zone panel. Yeah, I should say for radiant cooling, we also need humidity control, a dew point controller to make sure we don't undercool the floor and get condensation anywhere. This is what a system would look like with fan coils. If we added fan coils, very similar. Only over here, we have a separate branch that delivers to fan coils. Here's the previous system. This one here is if we're doing heating and cooling, it would have a seasonal switchover. That means sometime in May, you would the homeowner would switch it from winter to summer mode, and then from then on, the heat pump would chill the water in the tank as needed. And sometime in the fall, September, October, we would switch it back from summer to winter mode, and then we would start heating the tank again. So this would not allow simultaneous heating or cooling or in close succession, which is really not needed in a well-insulated modern home. A situation that we are heating in the morning and cooling in the afternoon really should not be required in a well-insulated modern home. So, but if we have a situation where we do need heating or cooling, maybe cooling on the south side of the house and heating on the north side or on the lower level, we still partly underground basement still needs heating, where the upstairs might soon need cooling. We can do a system here with basically two tanks, one hot tank and one cold tank. And then, so the heat pump would send the hot water to the larger tank and the chilled water to the cold tank, the smaller tank. And that allows a little more flexibility if that was required. Quick word about domestic hot water. We get that quite a bit. People are used to having their boilers provide space heating, but also domestic hot water. Because our output temperature is limited to 125, our domestic hot water recovery is rather slow. In addition, when we size our heat pump for our heating load of the house, it would be undersized if we also wanted it to make domestic hot water. not necessarily during the mild shoulder seasons, but in the depth of winter, when it's really bitter cold, you don't want to have to choose between taking a warm shower or having a warm living room. And so, if we wanted to make domestic hot water, really effectively, we would have to add a second heat pump. In addition, we would need a specialty tank, as shown here, with a domestic hot water coil. These tanks are very expensive, add additional cost, but then it's only a preheat tank, at 125. A lot of folks are looking for domestic hot water at 140. So we would need an additional water heater in series. And then if we wanted to do cooling, also, we certainly can't switch over this domestic tank because we don't want to chill our domestic hot water, pre-chill our domestic hot water. So then we would need a cooling tank, and it gets more and more expensive as we go along. That would make a really expensive domestic hot water heater. So this does not make sense to do, financial sense. What we are much rather recommending is one of those standalone heat pump hot water heaters. They are also very efficient and very reliable. They are available at a fraction of that cost. Plus, there's nice utility rebates available for those. The only problem with those is that we don't sell them. It's someone else's business. Very good. Here, I'm just showing another one. Another piping diagram. Heat pumps can certainly be staged. If we have a larger load, we can have up to 4 heat pumps. That's what our controller is able to handle. And staging means, the controller brings on one heat pump first, and then looks at the water temperature in target water temperature. If the one heat pump is not able to keep up, then it will bring on the second one, the third one, and possibly the fourth one. It can also we can also bring on the that's the same way the backup would be brought on as well. This drawing here shows a gas boiler for backup. Those are certainly available. Still works also quite well. Some people, they still like to have a gas range in the kitchen, a gas fireplace. So there is gas in the house. The question might come up, would it make sense to also install a gas boiler for backup? It's possible. If that's a good fit, that can certainly be done. But I should point out that the majority of our clients, they want to go all electric, and they would prefer an electric boiler instead. The electric boiler also does not have a vent pipe, so it's less holes in the envelope, less complexity, and certainly no gas leak. All of these things, no worries about carbon monoxide. So that certainly there are additional advantages to going all electric. A few words about challenges. Certainly when we are replacing our gas line with electricity to heat our house, it makes sense that our typical 200 amp electric service that we have in a typical residence, that might not be sufficient. If you're going all electric with an electric kitchen, maybe a double oven, cooktop, induction cooktop, then electric dryer, heat pump, and electric backup, and then we're adding an electric car charger, a fast charger. We would certainly be exceeding the typical 200 amps. Yeah, there are ways to extend it that make it work with 200 amps, for instance, by adding batteries. Yeah, the batteries are basically used yeah, only when we're exceeding or we're getting close to our 200 amps to make sure that the main breaker doesn't flip. But that probably is only going to be like a band-aid interim solution. So yeah, moving forward, yeah, I think the modern future-ready home will have 350 or 400 amps, depending on what's available from the utility. Yeah, working on a lot of new construction homes, ordering 400 amp electric service right from the get-go as the house is being planned is really usually not a big deal. And yeah, if it's scheduled early enough. Similarly, yeah, if your power lines are up above ground on the telephone poles, adding additional capacity should also not be a big deal. Yeah, where it is a big deal is in homes that were built since about 2000. Yeah, so developments since about 2000, when most of the electrical service was put underground. There it can add quite a bit of cost. But there are also government incentives available to upgrade electrical service. And we'll be getting to that in a moment. Another challenge sometimes is the best location for a heat pump. Yeah, we're harvesting thermal energy from the ambient air. And so, yeah, the warmer location around the house are certainly preferred, because where it's warmer, as we learned before, we have larger amounts of thermal energy to harvest. So, yeah, south-facing orientation is usually the best for heating, yeah, in our heating-dominated climates. But yeah, many folks have their patio or their front porch on the south side. So in those cases, east or west are certainly also acceptable. We're just trying to avoid anything that's facing north, because that's where the snow and ice doesn't melt for long and for long times. And yeah, so we would see it probably a measurable reduction in efficiency and output on the north-facing side of a structure. Yeah, another important thing when placing a heat pump on the outside of a house is yeah, the effluent from defrosting. Because we are harvesting thermal energy from the ambient air, we can get some frost built up on our heat exchanger. And yeah, when that layer of frost gets too thick, it acts as an insulator and our heat pump capacity goes down. So the other heat pump senses that, and then it will go into defrost mode, where it melts that frost. And that meltwater has to be yeah, piped somewhere. If the heat pump is located in the gardens, then yeah, you just let it drain away. Yeah, it's not a big deal. But if the heat pump is close to a driveway or a walkway, then yeah, it should be piped away so that it does not generate yeah, an ice skating rink or a hazard. So this shows an example. Yeah, here there was this gutter drain close by, and yeah, they just installed a PVC pipe to drain it over here. It's just important to note that you need to install a heat tape in this, so otherwise it would freeze up and clog, and then not function anymore. Very quickly on operating cost. We get that question quite a bit. Am I going to save any money when I switch from gas to a heat pump? And the short answer is yes. previously to the recent natural gas price increases, we were about even with natural gas. But now, last January, here on the Front Range, people paid about $1.37 per therm, which translates to about 5 cents per kilowatt hour if it's produced by an 85% efficient, high efficiency gas boiler. Electricity here was still around 12 cents if we don't have time of use pricing. So if we compare those two, we've got a factor of 2.2 between those. That means if we have a heat pump that has a coefficient of performance of 2.2 or better or higher, then our heat pump would produce the same amount of thermal energy at a lower cost. Here on the Front Range, we can expect a COP of 3.2. That means our operating cost on average can be expected to be about 30% lower than natural gas. With those peak prices. It's certainly important to note that natural gas prices, they change with the seasons. They're most expensive when it's coldest, when you use the most. But then as it gets milder, it gets cheaper. But as it gets milder, our heat pump coefficient of performance also goes up. So we should still always have an advantage in terms of cost with natural gas. With propane, it's a very similar story, only that the difference is even greater. If you pay $3 per gallon of propane, and again, you have an 85% efficient condensing boiler, your thermal kilowatt hour is costing you about 13 cents. So it's even more expensive than a straight electric resistance heat at 12 cents. So any appliance, heating appliance with a coefficient of performance of 0.9 or greater, which is basically anything hairdryer, electric heat mats, or something like that, is going to operate at lower cost than this propane boiler. Compared to a heat pump with a COP of 3.2, our operating cost would be a third compared to that propane boiler. What we also get quite a bit is the question, so how about our carbon emissions? If I go to a heat pump, if I go to electric, how does that compare in regards to my carbon footprint? The answer is a little complicated, and when you really dig into the data, the government issued data, there are some discrepancies that I don't want to get into. But from a top-level perspective, the government issued emissions numbers for 2021. Says that to generate 1 kilowatt hour of electricity in Colorado cost 1.3 pounds of carbon dioxide emissions. This is a state average. There are certainly pockets like Holy Cross Energy on the western slope. They're already 50% renewable, so they certainly have a lower carbon footprint on their electricity. But if we compare that with the combustion of natural gas, 0.44 pounds. At 9, with a high efficiency boiler, or propane at 0.53 pounds per kilowatt hour. It basically requires a 300% efficient heat pump, so a COP of 3, to cause the same carbon emissions as the statewide average electricity. Now, if you have your own solar PV system and you generate your own renewable energy, your carbon footprint obviously is quite a bit less than that. And yeah, it depends on how much, what portion of your electricity you're generating yourself. Yeah, it can even be close to zero. Rebates and incentives, yeah, are available, and it's quite a maze. There are yeah, a lot of really good things are in place that homeowners can look forward to. The Inflation Reduction Act, although it was passed in August of last year, things are still being worked out. Yeah, there are quite a bit of funds available for a long time, for many years. Up to 30% of material and labor for renewable energy installations, including heat pumps. A lot of those details are being developed by the states. And so the state has to set up a portal with applications, and those things are still being worked out. But yeah, it looks like yeah, those are certainly here to stay. And even if you're purchasing your heat pump today and having it installed soon, you can apply for those rebates later, the tax credits. The state of Colorado also has tax credits, sales tax exemptions. There are quite a few utility rebates available. Again, Holy Cross on the western slope is certainly a leader there with very substantial rebates. And then, yeah, there are some municipalities that are also offering some rebates, and but yeah, as always, it very much depends on where you live, where your home is located. A really good website to yeah, do this research by state and municipality is desireusa.org. That's an organization, I think it's run out of North Carolina University. They are keeping their database up to date of all the rebates that are available. Yeah, we're kind of getting to the end, and we're right at 8 o'clock. Quick summary, yeah, heat pumps, air source heat pumps, as we learned, are a reliable, established technology. They are efficient, dependable, quiet, and cost effective. Today's refrigerants, yeah, are not quite where they need to be. They yeah, they have a high greenhouse warming, global warming potential. However, there's a recycling program is in place. So yeah, if a heat pump gets removed, like the refrigerator recycling program, yeah, it can't be just thrown on down the next landfill. It has to be recycled and the refrigerant removed and recycled. So the other program ensures that yeah, very little of that refrigerant escapes into the atmosphere and causes damage. But that said, I was just at a heat pump conference, and yeah, many different new refrigerants are in development, and we're going to see quite a few improvements and new products on hitting our market, yeah, in the next coming years. As we saw, heat pumps are required for yeah, to achieve a net zero energy home. they are required for a carbon neutral home or a low carbon home. In terms of comfort and heating and cooling comfort, they are very, very reliable and dependable piece of equipment that, in combination with a radiant floor in particular, generates a very comfortable indoor climate. Now you might ask, so what are the next steps if I wanted to consider looking into getting one of those hydronic heat pumps? What would be my next steps? So the next steps, they depend if you're building a new home or if you have an existing home that you want to convert from gas to electric. If you're building a new home, what we would do is we would start with doing a heating and cooling load computer simulation. We would plug your architect's plans into our software. It's called a so-called manual J, and that would tell us what size heat pump we would need. And then we would have a conversation. What are you looking for? Heating, cooling, radiant. What kind of a distribution system are you looking for? What is most cost effective? What meets your goals? And then we would provide you with a system proposal for a system that meets those requirements. If you have an existing home that you would like to convert away from natural gas, what we can do is we can analyze your past gas bills, either your natural gas or your propane bills, and from that we can calculate what your energy load, heat loss is on the coldest day of the year. What we will also recommend is that you have an energy audit done, because obviously if you, going back to the envelope and the home as a system, you may want to take that opportunity, if you haven't already, improve the energy efficiency of your home, make it tighter, better insulated, because you might be able to get away with a smaller heat pump and also less operating time. We would again have that discussion with you. What are your goals? What are you looking for, or what you already have maybe in your existing home in terms of distribution, heating, cooling, and then provide you with a proposal just the same. Very good. That is, Kirsten, that is basically the end of my presentation. So thank you very much for attending, for listening, and we can move over to the questions.
All right, Hans, it's been great. If you want to pop up great. You got your slide with your contact information. Thank you.
Exactly. This is my contact information. I would just ask people to please be patient with us when you contact us. We're quite busy. Contrary to popular belief, we are not sitting on the beach with our gin and tonic and waiting for the phone to ring. No, we are very busy already helping other people electrify their homes.
All right. Well, and good qualifier, Hans. It's heat pumps are, excuse the pun, a hot topic right now. So let's jump into the Q&A, because you've got quite a few folks that are interested in getting your opinion on a few things. I'm going to start with Steve, who asked a question right at the beginning. I'm moving to a very windy place with lots of dirt blowing in the air. How does air source heat pumps, how do they do in that environment?
Well, so I mean, yeah, if you have the literal sandblasting going on, then there are certainly things that can be done to prevent that from destroying the heat pump over time. Installing a snow fence around it, something like that, shrubbery, to shield the the heat pump from that. Um, Sandblasting. But other than that, it's really not a concern. Wind is actually good. It's beneficial because we have more mass flow of air passing by the heat pump, and so I would say it should not be it should not have any detrimental effects.
Okay, thank you. Moving on to the next question. This is from Jill. So disappointed that heat pumps are not compatible with hot water baseboard. Are there any renewable or electrified solutions for hot water baseboard systems? And you can always punt on these too if it's not directly related, Hans.
Sure. Yeah. Um, so a hot water baseboard is a real challenge. On one side, it requires high water temperatures, and because of those high water temperatures, hot water baseboard is also not a very comfortable type of distribution system because it heats the air, and the air then immediately rises to the ceiling, and then it starts heating the room from the ceiling down. So what a lot of people describe their sensation is that they have a hot head and cold feet with hot water baseboard. So the question is that, and hot water baseboard was also installed, in the 80s, 90s. Home construction was not, overly high quality, I would say. Is it worth spending a lot of money on that house? So that is certainly a question that an energy audit would be able to answer. Even if our heat pump was, what I'm saying is that even if our heat pump was able to provide that hot water, at least the comfort issues would not go away. People have tried to increase the output of hot water baseboard, doubling up on the fin tube, and adding more linear feet of fin tube. But you would have to increase it fourfold, something like that, in order to get anywhere near the same output. So you don't even have enough wall space to do that. I'm being told, that in a few years we will have access to heat pumps that will be able to provide 150, 160, 170 degree water temperature, presumably. Maybe that is something that I would recommend is waiting a few years. What you could certainly do is get an electric boiler. Electric boilers are able to produce higher water temperatures, and then you would just have to install 3 times as many PV panels in order to get to the same renewable energy generation. Neither of that is cost effective. So I'm basically just thinking out loud, throwing some ideas around. It's because I don't have an easy solution. That's the thing. At this given moment, and in the near future, there is no easy solution.
Well, I think, Hans, that's a fair answer, that you're not going to have answers for everything. So let's keep going through a few more questions here. From Barbara, we've got, could you comment a bit more about staple up radiant heating? She has a propane-fired BCRES boiler, providing heating and water, providing heating with a water glycol mix. It's been working fine, now 16 years old, but would like to go to electric.
Yeah, so if it's a 16-year-old staple up, then it could still have those staples. It's possible that they already use those aluminum heat transfer plates that make it more effective. We would have to take a look at the boiler settings. What is the water temperature that it's running at? Is that something that we can get close to with our heat pump? That is certainly, I would say, that is certainly at least it's significantly closer to our reach with what we could do. I believe so.
Okay. That was kind of a very, very specific question. Let's go on to something a little more general here. And this is asked by Robert. What is the supplemental heat? That probably refers to something specific within your slides.
Yeah. So yeah, you have several different options. The other most popular among our clients are the electric boilers. Yeah, so basically, it looks like a shoebox mounted on the wall that has relatively big copper wires going to it. Because depending on the maximum output that we're looking for, it can draw 50, 60, sometimes more amps at 240 volts. And it's basically one of those countertop tea water kettles in a different box mounted on the wall, connected to our hydronic system. And when called for, it will activate and then heat the water. These are relatively low cost, dependable supplemental heat sources that they don't have any standby losses or any wear and tear if they are not running. If you still have gas at the property for other reasons, then you could certainly have a gas boiler for supplemental heat. Sometimes we get the question, how about a solar thermal system? Maybe you already have an existing solar thermal system. Our experience has been that if you don't have a pool you can dump solar thermal energy into during the summertime, we would certainly not recommending a new solar thermal system today. Simply because solar thermal generates a lot of the output during the summer months when you don't need it for heating your house. And so that investment would sit idle. Compared to solar PV panels, they would generate electricity even if you're not consuming it. At least your meter would spin backwards and you would get credit. And other than that, some people say we have a wood stove. We're happy to use when it's -10 degrees. We don't even need a backup unit at all. We would certainly tell them, you have to be home in order to load up your wood stove and maintain it. So if you like to travel for weeks on end, then that might not be a good choice. But we certainly have some clients who said, we don't need backup. We have a wood stove and we're done.
Hey, great. Gonna keep moving along, Hans. You're taking it on the fly. This is great. There's a gentleman, Robert. Robert, I'm going to suggest you reach out to Hans through the email that he's provided. with this great comment. It's a question about being from Germany, so I'm going to let you guys connect maybe offline and try to stay a little more focused on some general questions here.
I was not able to hide my German accent.
No, you're a carbon copy of Martin Volker here. All right, who's on the call? All right, let's move on with Kevin's question. Can a heat pump water heater be sized for both radiant floor, approximately 1,000 square feet, and domestic hot water?
So you're asking heat pump hot water heater. So one of those standalone, so not one of our heat pumps that sits outside, but the unit that is in the utility room. That certainly would not, you would not be able to use that for space heating because, yeah, you're absorbing thermal energy from that room and you're dumping it into your living room. That means you would be freezing up your utility room. And yeah, to a certain point, your living room would be nice and cozy, but then as the temperature in the utility room drops, the performance of that unit would go down. And then at one point it would say, sorry, it's too cold in here, I can't work anymore. So that doesn't work. You can't use, at least the heat pump hot water heaters, the standalone single units that are located in the mechanical room. You can't use that for space heating. They work really well for domestic hot water heating. That said, there is one unit, the Sandon unit, that has an outside evaporator, and so it's basically an air source heat pump that harvests thermal energy from the outside, similar to the Arctic heat pump, and heats the domestic hot water in the tank. And you can certainly use those. People have used those both for domestic and for space heating. They do have a limited output. So they don't, I believe they don't come in sizes as large as the Arctic heat pump. And they're also significantly more expensive. But that certainly could be an option. In case you were asking about our heat pump, used for radiant and domestic, we talked about that before. It's not cost effective. It's at this point you need so many accessories. It's simply not cost effective. I'm not comfortable recommending that because it's just not a good deal for a homeowner.
All right. By the way, I'm skipping through a few questions. Some folks that were attending have left the session here. Hans, I can send you a list of these questions tomorrow. You're welcome to reach out to some of these folks who might have asked questions that were great questions, but they're not on the call any longer. Let's go on with another question. A gentleman, Robert. Maintenance, longevity question for heat pumps. Will heat pumps last as long as my old energy inefficient 30-year-old gas furnace system? So longevity.
Mm-hmm. A very good question. So at least the heat pumps that we are selling, they have not been around for 30 years. So we don't know if they will last 30 years. The longest running unit that we have has been in operation that I designed has been in operation 4 years, and it's going strong. We're not stressing that equipment. We are not asking it to generate extreme temperatures, pressures, and so forth. I'm certainly expecting a good 10 years of life out of these units. What I like to point out is we are at the beginning of the heat pump golden age. Yeah, just in the very beginning. Yeah, there are billions of dollars are invested in heat pump research and development. Not only different refrigerants, but also efficiency, electronics, controls, and so forth. And so I would expect that if you were to buy a heat pump today, once that is 10 years old, it might still go strong, but you might have access to new heat pumps in the marketplace they might be twice as efficient as the one that you have. And so similarly to you replacing a car that has 150,000 miles on it with a more efficient one, you might also want to consider getting a new heat pump if it has additional features or is more efficient than what you already got.
All right. Are you ready for a couple more, Hans?
Sure. Yeah.
All right. Doing a great job taking these on the fly. And I appreciate your being succinct, because we do have a few questions that are great, a lot that we won't be able to get to. But from Martin, our dear friend Martin, he's our CRES chair. He asks, I'd like to note that do-it-yourself installing in-floor radiant heating is very affordable and quite easy, but professional charges are very high. And his question is, what kind of flooring works best?
Mm-hmm. Hello, Martin. Yes. If you go to the Arctic website, arcticheatpumps.com, you will notice that they're, at least at the headquarters, they're somewhat catering towards the DIY. They offer packages, and because you don't need any specialty tools, you can certainly, if you're handy, if you've done plumbing before, there's a good chance that you will be successful at first try installing an Arctic heat pump yourself. It's not necessarily something that we encourage, but it can certainly be done. And the same with Radiant. There, you can buy the other components, and there's instruction videos how to do it online. And we're happy to help, but just please don't expect us to come out and finish your job if you started and at one point you don't know how to finish it, or things are not working. What type of flooring? The only let me answer it this way. The only thing that we don't recommend is anything that resembles carpet, because carpet is an insulator. In particular, the traditional plush carpet with a big carpet pad underneath. That is basically does not work well with radiant floor. But any hardwood, engineered wood, there's some what's it called, luxury vinyl that's available now. Cork. We see a lot of polished concrete floors now in modern homes. So any of those. Even the floor tiles, the thin, quarter-inch thick floor tiles, or area rugs are also acceptable, certainly. But in general, before you buy flooring material, you want to talk to your flooring people, because some manufacturers say their product is not, they don't offer a warranty if it's used with radiant, which is really not um, yeah, it's not something that I hear a lot. That I can't understand why a radiant floor, in particular, if we run 100, 110, 115 degree water, why that would destroy a floor. If you have the same floor in front of your sliding door and the sun hits it, it gets warmer than that, a lot warmer. So why would a radiant floor from underneath damage your floor? It's beyond me, but I'm not selling flooring. I'm selling heat pumps.
Well, we're bumping up against our closing time. I'm gonna just jump over, and again, Hans, I can send you these questions tomorrow. You can see who's asked what, and maybe get back to some folks, as you have time or your team has time. I think this is a great. By the way, the very last comment was, "Thank you, great presentation" by Kevin. Uh, but
Okay,
Ryan
thank you.
asked, yeah, well, hopefully he'll listen to this all the way to the end tomorrow when he listens to the presentation online. This question is kind of nice. If you're talking to high school students, where should they go to get trained for you?
Well, I think it certainly depends what their ultimate goal is. Where but if they just want to learn about the heat pump installations, um, I
You can
mean,
always punt
we
too, Hans. I mean, if you don't have any direct, places to go to get trained. This is, like you were
yeah.
saying earlier, it's new technology. This is very new. It's very exciting. People are really wanting more information about it. There's IRA money. There's a lot going on. If there's not a direct answer, you're welcome to
Well,
punt.
I was going to say, that you don't have to go to college. You can go to join the trades. There's a lot of money is made in the trades. As Martin mentioned, in his question, um, labor cost is significant, and so you don't have to go to college to make a really good living. Um, and if we wanted to convert all 120 million homes in the U.S. to heat pumps, that's a lot of work. That's it's going to keep installers busy for a long, long time. So I don't know if installers offer kind of apprenticeships. Uh, yeah, Opportunities for high school kids to maybe during the Green Home Tour, the Green Building Guild in the fall, it might be a good opportunity. For instance, those are my ideas. But
Well, I think that's great. And again, you don't have to have all the answers. You've done a great job fielding the questions, and your information is here on the last slide, and we will be again sending this out to everybody who's registered, along with those who attended. Uh, Hans, thank you so much for taking your valuable time tonight and jumping on here with us. And we look forward to hopefully doing this again with you maybe next year, because this is an exciting, really burgeoning field, and we look forward to talking with you again and uh, Thank you so much.
Well, thank you, and thanks everyone for joining us. Yeah, have a nice evening, everyone.
Okay, take care.